You know that feeling, right? Staring at a page full of the laws of sets, trying to cram them all in before a big exam. It's a classic struggle. But what if I told you you didn't have to memorize them at all? In the next few minutes, we're going to make these laws so intuitive, you'll literally be able to build them from scratch whenever you need to. Let's dive in.
Okay, so you see this on an exam paper. And for a lot of people, the first instinct is a little bit of panic. It looks complicated, abstract, and just one more formula you have to shove into your brain. But that thing right there, it isn't just a rule to memorize. It's actually a picture. And that's the whole secret.
And this, right here, is the absolute biggest mistake people make, treating these laws like there's some poem you have to recite. It's inefficient, it's super stressful, and it doesn't actually help you solve problems. So let's ditch the flashcards. The goal here isn't to memorize, it's to understand, so you can derive any of these laws on the fly.
So, to get started, let's connect all this to something you already know inside and out. A lot of these laws of sets, well, they follow the exact same logic as basic arithmetic. They're not nearly as scary or as new as they seem at first glance.
First up is the commutative law. The core idea is incredibly simple. The order just doesn't matter. Combining set A with set B gives you the exact same result as combining B with A. You know, it's no different than saying that 2 plus 3 is the same as 3 plus 2. Same thing.
The associative law kind of builds on that. It just says that when you're doing the same operation over and over again, like all unions or all intersections, it doesn't matter how you group things. Combining A and B first and then adding C, it's identical to adding A to the combination of B and C.
Now, this brings us to one of the most useful connections of all, the distributive law. Just like in algebra, where you distribute a number across what's inside the parentheses, you do the exact same thing in set theory. That A-intersect operation gets distributed over the union. It applies to B, then it applies to C, and that union sign in the middle, it just stays right where it is. It's really that simple.
All right, time for the big one. This is the law that for some reason just loves to show up on exams. It looks intimidating, I know, but once you learn this little visual trick, it becomes one of the easiest ones to solve. Let's finally crack De Morgan's law.
So what's the trick? How can you look at this thing and solve it correctly every single time, especially when you're under pressure?
Okay, here it is. It's a simple three-step physical action you can do in your head. You start with your expression. Then, you literally imagine physically breaking that complement bar over the top, so it covers each letter inside. And now the crucial final step. You change the sign in the middle. The union flips to become an intersection. That's it. That's the entire trick. Just say it to yourself. Break the bar, change the sign. This little phrase works for both of De Morgan's laws. If there was an intersection in the middle, it would just flip to a union. It works perfectly every single time.
But why does this little trick actually work? Well, it's not magic, it's just a shortcut for a visual truth. So look at the left side, the complement of A union B. That just means shading everything outside of the two circles put together. Now look at the right. We're looking for the intersection of not A and not B. That's the area where everything that is not in A overlaps with everything that is not in B. And as you can see, those two shaded regions are exactly the same. The mnemonic is just a faster way to get to the proof.
All right, to round things out, let's just blast through a couple more simple laws, and then I'm going to give you the ultimate hack for when you get truly stuck on a proof.
The idempotent law. The name sounds way more complicated than the idea. It's simple. Combining a set with itself doesn't change anything. I mean, think about it. A set is just a collection of unique items, so taking the union of A with itself doesn't add any new items. It's still just A.
And then you've got the identity law, which gives us our version of the number 0. The empty set, this little symbol here, is just like 0 in addition. If you take any set A and add nothing to it, by taking its union with the empty set, well, you're just left with A.
And now for the ultimate safety net. If you are ever in an exam, you're feeling the pressure and your mind just goes totally blank, you have one foolproof tool you can always fall back on. Just remember this: when in doubt, draw it out. The Venn diagram is your absolute best friend.
Here's how you use the hack. You take the left side of the equation and you shade the region it represents on a Venn diagram. Then, on a totally separate diagram, you do the exact same thing for the right side. If the final shaded areas are identical, boom! You've just visually proven that the law is true. It is an undeniable way to check your work.
And there you have it. No more memorization. You now have the visual tools to actually understand and prove the laws of sets. So the only real question left is,
Which problem are you going to solve first? In our next explainer, we're going to take these exact skills and use them to break down those long, confusing word problems using the inclusion-exclusion principle. I'll see you there.